I'm a professor here at Brown in the mathematics department, and I'm the director of ICERM. ICERM is the Institute for Computational and Experimental Research in Mathematics. We are a math research institute funded by the National Science Foundation, the Simons Foundation, and individuals and academic sponsors. Our mission is to bring people together to do mathematics in groups. Mathematics is not a solitary activity. Mathematics is best done with other people who are excited about mathematics. We aim to create an environment where communities can come together and do exciting and interesting things. And so we're really happy to have you here tonight. ICERM's niche is computational experimental mathematics, which means doing computations, computer experiments to try to figure out what's true before trying to prove it, but also looking at algorithms and other computational outcomes of mathematical results. And so that feedback is something that we try to encourage in everything that we do. So we are really grateful that you're here tonight. This is actually our first in-person public lecture since the pandemic. I think it's been close to almost 3 years since we've done this. A little rusty, a little nervous, but it's really, we're grateful that you all came out tonight and less than inclement weather to join us. Let me say a few words about Professor Rich, who is our speaker tonight. Sometimes people ask me, how do you choose public lectures? And usually I don't have a clear answer, but here I do. And I hope I don't embarrass either the lecturer or my children by telling the story. So one time I got up early in the morning and my 10-year-old had been watching YouTube and he said, "Dad, do you know about the 3x plus 1 problem?" And then he proceeded to give a mathematically precise description of the 3x plus 1 problem, which I will not repeat because it's not a talk. And I was stunned and amazed. And I said, "Where did you learn this from?" And he said, "YouTube." So my curiosity was piqued. So I went and he showed me his YouTube video, and I saw Professor Calderón talking about the 3x plus 1 problem. I said, well, if my 10-year-old can get that out of a YouTube video, he has to give a public lecture. That's a qualification enough. But I guess I should say there are some other qualifications for his giving a public lecture other than impressing my 10-year-old son. He's a former colleague at Brown. He was a market assistant professor for 3 years. He is one of the best supporters of ICERM as an institution. I went and checked, and he has been here 8 times as an organizer, as a speaker, as an attendee. And so people who come back and take on leadership roles at the Institute, we're really grateful for them. And so I feel a little guilty to prevail upon him to come again for the 9th time, but he's really someone that supports the missions of the Institute. He's a managing editor of Experimental Math. I actually knew him through the editorship before the YouTube video. So it's not completely through YouTube that I was aware of his work. He has gotten many, many distinctions for his research. He's one of the world's leading experts on Apollonian circle packings, which is an important topic at the interface of dynamics and number theory. He's done very fundamental work in that area. He's also a master of exposition. He is it the Dean of Mathematics? I don't know the exact term, but there's a museum of mathematics in New York City, National Museum of Mathematics. And he has a leadership role in providing materials and information for the public. And so he's a real leader in our community to try to explain what mathematicians do to the widest possible audience. He's a professor at Rutgers, I guess I should mention that too, and he's won many, many awards. He's a Sloan Foundation Fellow, Cobley Fellow. He has gotten lots of NSF awards. I won't go on. They're all in the bio, but he's a great mathematician, a great expositor, and we're really grateful to have him here to speak to us tonight. Mary, you're on the wall. Thank you, Alex.
So thank you so much, Brendan, for that very kind introduction. I didn't realize I'd been here that many times. It does always feel like home, so you sort of don't even notice. Since, as Brendan said, I was here for a postdoc. Thank you all for coming out tonight and braving the weather. I want to tell you a little story about mirrors. So does anybody know this painting? This is a Norman Rockwell girl in the mirror. So what is a mirror? Mathematically speaking, of course, everybody presumably you looked in the mirror sometime today, maybe you woke up and brushed your teeth or something, looking yourself in the mirror. What's really going on is that a point like this is moving across the mirror, and it's moving twice the distance to the mirror. So if this is the distance to the mirror, it moves to a spot that's on the other side of the mirror that's exactly the same distance as it was away from the mirror. That's mathematically what a mirror is, but of course mirrors are much more fun when you, as Brendan said, mathematics is more fun with the company of other mathematicians. That's what ICERM is here for, and mirrors are more fun in pairs and in collaboration. So let's collaborate a couple of mirrors. So here you have just a pair of mirrors. They've been hinged together, glued together. ICERM was kind enough to provide this. And this is, anybody know what shape this is? Maybe the youngsters can tell us. The professional mathematicians are not allowed to answer these questions. Please. What's this? It's a triangle, yep. Any kind of special properties of this triangle? It is isosceles, two sides are the same. It's also right. One of the angles is a right angle. Okay, so here's your first pop quiz for the night. I'm going to take this isosceles right triangle and I'll put it into the pair of mirrors and we're going to look inside. And the question is, what will we see when we take this isosceles right triangle and put the 90-degree angle into our pair of mirrors? So you can shout out answers or you can hold up your hand. Okay, we have one vote for square. Any other suggestions? Any other thoughts? I guess there are a lot of professional mathematicians here who are sitting on their hands so as not to reveal the answer. How many votes for a square? Okay, a small handful. How many votes for maybe something else that you don't want to reveal? Okay, and most people aren't voting. That's democracy. All right, well, let's see what it is. So the only votes that we've seen so far are for a square. So as you can see, I'm putting the right angle in, and if we look inside, maybe I'll stand over here. If we look inside, can everybody see that? So indeed, we get a square. We get a square when we do that. Now, why do we get a square when we do that? What are we actually seeing? So what we're seeing is when you put that right angle of the isosceles right triangle into the 90-degree pair of mirrors, the image is reflected across each of the mirrors, and it's also reflected along the back mirror, which is an imaginary mirror. So when you unfold this triangle across all of the reflections of the pair of mirrors, you indeed get the square, and that's the symmetries down the diagonals, down the two diagonals of the square. Okay, does that make sense? All right, a slightly harder one. Now instead of putting the 90-degree angle in, I'll put the 45-degree angle into the pair of mirrors. Now what will we see when we look inside? Any votes for anything? Yes? An octagon? We got a vote for an octagon. That's a very, very good idea. Other ideas? Other suggestions? Things that you might see? What's that? A star shape? Okay, we've got a star shape. We've got an octagon. Any other suggestions? And if you've taken out some paper and started doodling, that's mathematics. All right, we've got votes for octagon and star shape. So how many votes for octagon? Okay, there's a handful, quite a number. I can't count that high. How many votes for star shape? Okay, quite a number. Votes for something else? Okay, there's a couple of votes for something else. Let's see. That's what the survey says, but we don't go by surveys. We go by mathematics. So here I have, hopefully you can see, the 45-degree angle is being put into the mirror, and what will you see? You still see a square. So why do you see a square? That's the interesting thing. Why do you see a square? Well, again, we're putting this 45-degree angle in, and when we unfold everything, when we unfold that triangle across this mirror, when we take its image across this mirror, across that mirror, across all the other mirrors, we would get an octagon if this was an equilateral, if this was an isosceles triangle with the two sides being the two sides that are going in. In other words, a 45-degree angle where the two equal sides go in. But because there's a right angle here, even though this is 45 degrees, 45 is a quarter of a straight line, a straight angle is 180 degrees. 45 is a quarter of that. So of course, there are 8 copies of this triangle around this corner where the mirrors meet. But because there's a 90-degree angle, 2 of those copies get glued together into one straight line. So that's why you're seeing a square and not an octagon. An octagon was a very good guess, but it turns out. So what are we really seeing here? We're seeing the full group of symmetries of a square, the diagonal symmetries that we already saw, and of course there's the symmetries down the midpoints of the sides, the vertical symmetry and the horizontal symmetry. Okay, very good. Ready for another one? All right. Now I'm going to take this triangle. Do you want to tell me what this triangle? So it's a triangle. We still have a right angle. I don't know if you can tell what the shape is, what the angles are. Does someone who's not a professional mathematician know what shape this is? It is what? It is scalene. Yeah, all the sides are different, but it still has a special structure. One of the sides, you can't read this. One of the sides has length 1, one of the sides has length 1/2, and one of the sides has length √3/2. So that's a special kind of triangle. 30, 60, 90. Beautiful. So this is a 30, 60, 90 triangle. And the question is, when I take the 90-degree angle and I put it into the pair of mirrors, what will we see when we look inside? Okay? So if you need some paper, I don't know, I guess we didn't pass out any paper, but some of you, somebody is working on some paper and pens. So tell me what you think we're going to see when we look in here. Any ideas? I'm putting the 90-degree angle. The 2 mirrors will be at a 90-degree angle. We're going to look inside and see what we find. A rhombus. Okay, we have some votes for rhombus. Any other thoughts? Keep working. I don't want to interrupt. You have an idea? You want to tell us what you're thinking? A diamond shape. That's very interesting. A rhombus. Well, okay. Yeah, a diamond shape, rhombus. Other ideas? Shall we have a look? So, again, when we take the 90 degrees into the pair of mirrors, and we look inside, we see a rhombus, a diamond. That's exactly right. So you guys are getting good at this. So why is that what we see? That's because you guys are getting good at unfolding this shape. And here are the 4 images. There's a 90-degree angle, so there's only going to be 4 copies of that shape. And that hypotenuse gets mapped around. But now it's no longer in a square. It's a squished square. So it's this diamond rhombus shape. Okay, fine. But now we're going to take, of course, the 60-degree angle, not the 90-degree angle, but the 60-degree angle, and put that into the pair of mirrors. And now it gets interesting. What will we see? When you take your 30, 60, 90 triangle, you put the 60-degree angle into a pair of mirrors and look inside. What will we see? Yeah, you have a suggestion? Okay, we have a vote for equilateral triangle. That's an interesting option. Others? A parallelogram. Okay, we have equilateral triangle and parallelogram. A hexagon. A hexagon's a very good guess. We have equilateral triangle, parallelogram, and a hexagon so far. Any others? What's that? I thought I heard someone. Okay, you ready to see? Let's see what it is. So again, we have our 30, 60, 90 triangle. I'm putting the 60-degree angle inside the pair of mirrors, and we get an equilateral triangle. An equilateral triangle. Well done. Well done. So how did you know that you were going to see an equilateral triangle in there? Yes, exactly. Very good. Very good. So the reason we're seeing equilateral triangle is that it should be a hexagon, because there's 60 degrees, and 60 degrees is a third of a straight edge. In other words, a sixth of a full circle. And as you reflect across the first mirror, across the second mirror, and continue the reflections all the way around, you would be getting a hexagon if you didn't have this 90-degree angle here that's turning two of the lines into a straight line, and the resulting image is an equilateral triangle. And in fact, again, the mirrors are revealing to us the symmetries of an equilateral triangle, which if I have an equilateral triangle, I can cut it down the middle. And that's certainly a symmetry, but there's three middles, and all three of those middles are exactly what we see when we cut the triangle into its symmetric component. All right? Well, there's one more angle, so obviously what I'm going to ask you is, if I take the 30-degree angle and stick it into a pair of mirrors, what will you see? Yes? A hexagon? Why do you say hexagon? Beautiful, beautiful. Okay, so just to repeat that, you're telling us, sorry, what's your name? Iris. So Iris is telling us that because it's a 30-degree angle, 30 degrees is a sixth of a straight angle, which means straight angle meaning no angle at all, which means there are 12 copies around. So you might think a 12-gon, but there's a 90-degree angle, so you're expecting half of that. You're expecting the hexagon instead, and that is a very good, you guys are getting really good at this. So here's again the 30-degree angle, the pair of mirrors, in it goes, and there's your hexagon. Okay, so you guys, now you understand pairs of mirrors. I think we understand everything there is to understand about pairs of mirrors, because what can you do? You can take, so again, if we put that in, here's how the image unfolds as light hits all the components, and indeed we get a hexagon. So with a pair of mirrors, we can always, if we have those mirrors at an angle that's 1 over a sixth or a third or a quarter, 1 over a whole number of a straight angle, so 180 degrees divided by n, for any number n, we will see the symmetries of your favorite regular n-gon will be revealed by having your pair of mirrors meet at an angle which is 1 over n of a straight angle. In other words, this is a sixth of a straight angle. Okay? So that's with a pair of mirrors. And now we've understood that, we can move on to a more complicated question, which is, what is a kaleidoscope? So hopefully you've all played with kaleidoscopes as kids. You have a tube, you look in it, and you move it around, and there's these funny patterns happening. So this is a typical picture inside a kaleidoscope. What's actually going on here? So it has to do with mirrors. That's what the whole talk is. So a bunch of this is just imaginary. It's not actually there. Where is the bit that's real? What's the actual image? What's truly there, and what is reflection? What's that? Did I hear someone say something over here? You can say. It looks like a piece of pizza. Yeah. You mean because there's like a hexagon or something? It looks like there's one triangle that's repeated, and indeed, this triangle in here, that's the only thing that is real. Everything else is getting moved around, but how? In fact, I don't know how well you can see from where you're sitting, but this is one plate. Because you're putting it right up to your eye, it doesn't look like a rectangle. You're getting this perspective view on it, but that's one plate, and then there's a second plate over here and a third plate over here. So it's just three. So what a kaleidoscope is very simple. It's just three rectangles that are long and narrow that all meet at a 60 degree, the cross section is a equilateral triangle, 60, 60, 60 degree triangle. And when you look into here and you put some shiny things there, the light bounces off of the cylinder, at a whole bunch of random ways. And then your eye thinks that this bead is actually reappearing there and reappearing there and reappearing there and so on. So the beads get moved all around as you look inside that kaleidoscope. Okay, so far so good? Any questions? Please interrupt at any time, anything you want to ask about. So given that that's how the standard kaleidoscope works, we might ask, are there other kinds of kaleidoscopes? Maybe the toy store is not giving us everything that we should be, that we have a right to ask about. So what does that mean? So if we were going to construct another kind of kaleidoscope, we would want a triangle. So 3 mirrors. Those 3 mirrors, each pair of mirrors still needs to meet at 1 over a whole number angle, a fraction of a straight angle. Okay, so 180 degrees, by 1 over a, I mean 180 degrees divided by some integer a, some whole number a. Same thing at every angle. But the 3 angles in a triangle, if you don't know this fact, let me, because I don't assume that you know it, let me prove to you that the 3 angles in a triangle, hopefully you see here, I have an angle here, here, and there, and the 3 angles in a triangle, if you fold them up, add up to a straight angle. Okay, so this is the 3 angles in a triangle folding up to a straight angle. Okay, so just to remind you of that fact, we have some youngsters here, maybe you know that fact already, maybe not. So if you take the 3 angles in a triangle, 180 over A, 180 over B, 180 over C, should add up to 180 degrees. So now we're trying to understand what kaleidoscopes exist, so we're trying to understand what whole numbers, A, B, and C, greater than 2, because we at least want to fold the mirrors in half, what solutions are there, possible solutions are there to this equation. Should I give you a minute to think about it? You can solve this equation. You can solve this equation on your fingers. Now, some of you algebraic geometers are starting to do all kinds of fancy things, but in fact, the fancier you go, the farther you are from a solution. So let me try to explain how to solve something like this. So our equation is 1 over A plus 1 over B plus 1 over C is equal to 1. Okay? And we can assume, so again, 1 over A is representing, if this is some fraction, this is 1 over A of a straight angle. So there'll be A copies of this tile, A copies of that tile going around the angle to make 180 degrees. So we want A, of course, to be at least 2. So there's a symmetry between A, B, and C. We may as well order them so that 1 over A is the largest angle, 1 over B is the next largest, and 1 over C is the smallest angle. And so what's the largest we could make this angle? Well, the largest we could try 1 over A equals a half. Okay, so if we try just splitting the straight angle into 2 parts, and then what could we do? Well, 1 over B, if we want to make 1 over B as large as possible, bounded by a half, we can make B equal to a half itself. But then a half plus a half is already equal to 1. So there's no way to pick a value for C. So a half doesn't work. Okay, let's try a slightly smaller angle. Let's try 1 over B is equal to a third. Could that work? Yes, it could. A half plus a third plus a sixth is equal to 1. Okay, so that's one solution. Let me just write it as a half plus a third plus a sixth is equal to 1. Okay, great. Now let's try 1 over B is equal to 4. Let's see, I'm going to get too low for the people in the back. How about 1 over B is equal to a quarter? So could we do a half and a quarter and a quarter? Okay, a half, a quarter. Okay, so that's another solution. A half plus a quarter is equal to 1. Is this too hard? No, it's okay. Yeah, it's too easy, right? Yeah, you guys got it already. All right, so we tried a third, and a third worked, and we tried a quarter, and a quarter worked. What if we try for the second angle to be a fifth of a straight angle? Well, we said that 1 over B is going to be larger than 1 over C. So 1 over C, the largest we can make 1 over C is also a fifth. But a half plus a fifth is too small. So in fact, we can't choose any value of c. There's no value of c that will work for this value of b. In fact, there's no other value of b, because once you make b 1 over b small, then 1 over c is going to be even smaller, and there's no way to add up all the way to 1. All right, so that's all we can do for the first angle being a half. What can we do for the first angle being a third? Remember, it's the largest one, so I can't try a half anymore, because that's too big. So I can try b is equal to a third, and if I have a third and a third, this would be a third. Okay, so we have a third plus a third plus a third is equal to 1. Great. Can we try a quarter? Can b be a quarter? So this does give a solution. If we try b as a quarter, we have a third plus a quarter plus at most a quarter. That's already too small. So there's no smaller value of, I don't mean b, I mean 1 over b, of course. Please correct me. The mathematicians are allowed to correct me. They're not allowed to answer questions, but they are allowed to correct me when I write something wrong. So that's all we can do for a third. And if we try 1 over a as a quarter, or anything smaller, now I have something a quarter plus something smaller plus something smaller. There's no way I'm going to get up to 1. That's it. That's all the solutions. On our fingers, we solved this equation in the integers. Okay? So this is how arithmetic is informing geometry already. That simple questions about whole numbers that you can solve on your fingers in grade school tell us everything about the possible kaleidoscopes. So let's look at those kaleidoscopes. So our 3 solutions, we're going to count on our fingers. Our 3 solutions, we found a half plus a third plus a sixth is 1. We also found a half plus a quarter is 1. And we found a third, a third, a third. So what are each of those solutions? Well, what does this mean? We're trying to figure out an angle that's half of a straight angle. That's 90 degrees, plus 60 degrees, plus 30 degrees. That's our 30, 60, 90 triangle. But now we allow it to tile the entire plane. Okay? And in this tiling, notice that if you look around a pi over 2 mirror, that's that diamond shape, that kite that we were seeing when we took the pair of mirrors. Everybody see that? Around the vertex that had a 60-degree angle, here's our equilateral triangle with the 6 copies of the triangle going around. And there's a tiling of the entire space by those triangles. And of course, around the 30-degree angle, we see a hexagon, and the hexagon tiling the entire plane. Okay, so all those images that we saw with a pair of mirrors are still there. It's just there's lots more of them. They're filling up an entire plane instead of just going around a single vertex. Does that make sense? So that's what the 30, 60, 90 tiling is, a half, a third, a sixth of a straight angle. How about a half, a quarter? Well, that's 90 degrees, 45, and 45. That's our isosceles right triangle. And there are 2 kinds of squares. There's a square that has only 4 copies of the isosceles right triangle in it. That was when we put the 90-degree angle into the pair of mirrors. Or when we put the 45-degree angle into the pair of mirrors, we had 8 copies of the isosceles triangle. Both of these squares tile the plane, both of these larger structures. And then there's the kaleidoscope that everybody buys in the store, the 1/3, 1/3, 1/3 kaleidoscope, which is the traditional one. That's it. We just proved a theorem, and the theorem says these are the only kaleidoscopes that will ever exist in the history of mankind. Okay? Someone told me that they do make kaleidoscopes in these 30, 60, 90, and 45, 45, 90. I have never seen one, so I'd love to get my hands on. I mean, it's easy enough to build your own, but anyway, it'd be fun to play with these. Everybody always plays with the equiangular and equilateral kaleidoscope. Okay, great. Any questions so far? So far, so good. So we have classified, these are all the kaleidoscopes that exist in the plane, but we don't live on a plane. At least some of us don't think we do. We live on the surface of a sphere. So what should a mirror mean on the surface of a sphere? So ICERM was kind enough to provide this totally awesome chalkboard sphere on which we can do some experiments. So on the surface of a sphere, what is a mirror? Well, a mirror is going to be a circle that cuts the sphere exactly in half. Okay, that's called a great circle. And when you take a reflection across a great circle, you do exactly what you would do in a regular mirror. So hopefully you can see here, this is Mexico, and now we have two copies of Mexico, left-handed Mexico and right-handed Mexico. Okay, so that's what a reflection, a mirror across such a mirror would look like. And so what would a kaleidoscope on the surface of a sphere be if we took 3 such planes and we cut the sphere with 3 planes meeting at some angles? We would see, right here you see the 3 angles of a triangle on the sphere. So if you've never thought about spherical triangles before, just imagine standing somewhere at the equator, and if you go straight north, and then you turn 90 degrees, and you come down 90 degrees from this line, and you go back to the equator, so now you have 3 angles, and each of those angles is a right angle. At the equator I have a right angle, here I have a right angle, and at the North Pole I have a right angle. So that's 3 right angles, so the 3 angles of a triangle on the surface of a sphere add up to more than 180 degrees. Okay, so again, but locally we still want to have the mirrors give us a nice tiling around a corner. And so the mirrors will still need to have angles that are a whole number fraction of 180 degrees, of a straight angle. So now we're trying to solve the equation 1 over a plus 1 over b plus 1 over c, not is equal to 1, but is greater than 1. It looks like we have much more flexibility now, because it's not an equality, it's an inequality. We want to make these 3 fractions add up to more than 1. But as you'll see, again, there's a very short list of solutions. So one thing you could do is you can make 1 over a be a half, 1 over b be a half. We threw that out when we were looking at the sum of 3 things adding up to 1, because the next thing is going to make things bigger than 1. But now we want things to be bigger than 1, so we can take any solution, so a half plus 1 over n, for any value of n, 2 or larger, a whole number, is going to add up to more than 1. What are those triangles? Well, it's just an n-gon around the equator, a regular n-gon, and we know we can make a regular n-gon for any n we like. So around the equator, you have a regular n-gon, and then you just connect up to, are these longitude lines? Longitude lines, up to the North and South Pole as you go around. So here I have pi over 2, that's the 1/2. Here I have 90 degrees, that's also 1/2, and here I have 1 over n of a straight angle for any value of n. Okay, great, that's it. So that's an infinite family of solutions, but that's not surprising because we already knew we could make any regular n-gon we wanted. We also have a solution, so that was 1/2, 1/2 we threw out. 1/2, 1/3, when we were solving the equality equals 1, we had a unique value for c. But now we want something that's bigger than 1, so we can take we can take 1 over a to be a half, 1 over b to be a third. 1 over c, we can take anything that's more than a sixth. So as long as c is less than 6, we'll get a solution here. So that's a half plus a third. That's a 90, 60, 60 triangle, will be a tiling of the sphere. We can also take c to be a quarter. That's still bigger than 1. We can also take c to be a fifth. That's still bigger than 1. But once we take c to be equal to a sixth, that's a half plus a third plus a sixth. That's already equal to 1. And that's we need the sum of the angles to be greater than 1. So these are these 3 triangles. Now what about if a is a third? Well, again, if we order the sizes, if a is a third, then b is at most a third, and c is at most a third. The most that'll ever add up to is 1. And we want things to add up to more than 1. So that's it. Again, we've classified all of the possible kaleidoscopes on the sphere. So let me show you, let's get a little bit more familiar with what these kaleidoscopes are. So when I was at MoMath, they have this crazy contraption, which is a bunch of mirrors all meeting at the center. So imagine making these cuts into a sphere and cutting out a pie slice. And that's exactly what this pie slice is. And when you, let me try to start it again. When you take out this pie slice, so I'm showing here that these 2 angles meet in such a way that a bar turns into a triangle. That means they meet at 60 degrees, actually. They meet at 120 degrees, but never mind. And when you put this stick inside, the symmetry group that arises moves this bar all the way around to form the symmetries of a tetrahedron. So a tetrahedron is a solid shape with four. Tetra means four, like Tetris. Tetris is four squares that can move around. So this is a tetrahedron. There are four colors that can move around, and the symmetries of this object are exactly that first kaleidoscope, the 1/2, 1/3, 1/3 kaleidoscope. Our next kaleidoscope, here I'm showing you that you have a square side. That's because we have a 1/4. So the angles here, maybe this is too small for you to see in the back. This is a 1/2 plus a 1/3 plus a 1/4. So the 1/3 would be a triangle shape, and the 1/4 would be a square shape. And when you put a stick inside, what you see, hopefully you see this shape, which is called an octahedron. Octa means 8. There's 4 triangles on top, 4 triangles on bottom, but there is no top and bottom. Everything looks exactly the same. Okay, so those symmetries are the symmetries of an octahedron, and in the same symmetries arise for the dual of the octahedron, which is the very familiar cube. Okay, so those symmetries are this middle symmetry. How about this last one? Non-mathematicians, do you know what shape this will be? Without looking at the table to check what other shapes I have waiting. All right, let me show you. So again, we have a 1/3 angle here. We have a 1/5 angle here. That's why you're seeing a pentagon. And when I put the stick inside the pair of mirrors, there's a better stick to use for that direction. I get an icosahedron. So again, there's only one stick, right? The fact that you're seeing an entire solid shape is the illusion that that stick is getting moved around. And the dual to the icosahedron is the dodecahedron, which sits right on top of it. And there's just 2 sticks that are forming those shapes. So an icosahedron, icosa means 20. This is the shape when you have 5 triangles, 5 equilateral triangles meeting at every corner. There's 5 on top, 5 on bottom, and then there's Bart Simpson hair zigzag around. So there are 10 triangles here, so that's 20 total. 20 is icosa. So this is an icosahedron. And the dual of the icosahedron is this big guy, the dodecahedron. Dodeca is 12. There are 3 triangles on top, if you want to think about it this way, 3 triangles on bottom. Every corner has 3 pentagons meeting at it. So these are the regular solids that the ancient Greeks also, and many other ancient civilizations figured out. Their symmetries are exactly the only kaleidoscope groups on the sphere. And in fact, we could discover, if we didn't know the Platonic solids, we could discover them through this classification of kaleidoscopes. Okay, does that make sense? All right, so where are we? We have understood the kaleidoscopes, in other words, the reflective symmetries of the sphere and the Euclidean plane. So these things were known long before this gentleman, but this is H.S.M. Coxeter, a very famous geometer, lived most of his life in Canada. And he invented what are called Coxeter diagrams. So this is a diagrammatic way to capture all of the geometry instead of needing to draw these pictures, because once we get to higher dimensional spaces, which of course is where we're headed, we won't be able to see these pictures anymore. But he realized that there's a diagram that will capture all of the information for you. So here is what the diagrams look like. I'm not going to give you a whole course on how to read these things, but remember this is a 1/2, 1/3, 1/3. So here's your 1/3, 1/3, and the halves you don't connect. Well, here I am teaching you how to read these things. This is a 1/2 and a 1/4. I'm sorry, a 1/3, a 1/4, and the half you don't connect. This is the half that you don't connect, a 1/3 and a 1/5, a 1/2 plus a 1/3 plus a 1/5. That's that symmetry. This is a 1/3 and a 1/6. So that's the 1/2, a 1/3, a 1/6 triangle, the 30, 60, 90 packing of the Euclidean plane. Here you should maybe start to see 45 degrees, 45 degrees, 90 degrees. And here's a nice little coincidence that the equilateral triangle has a Coxeter diagram, which is an equilateral triangle. So that's the tiling. These are the Coxeter diagrams. Doesn't matter what they are. There's some diagrammatic way that you could represent all of these without needing to draw the full symmetry. And that'll be very useful because what Coxeter figured out is that these simple 2-dimensional pictures allow you to understand all dimension spaces and their reflective groups. So here's what he figured out, and this is about 90 years ago in the Annals of Mathematics, one of the top journals in all of mathematics. He gives these 2 tables. don't worry about what the tables are. They're tables of these diagrams, these Coxeter diagrams. And this mirror, the girl in the mirror, is just a single mirror. Just it's not interacting with anything else. That's called A1 in his. That's where that mirror is in his diagram, A1. Then we have a triangle at 45 degrees is over here, and then the spheres that we were looking at. So this is the tetrahedron. Here is the octahedron, and here's the icosahedron. Everything else is the same except this thing that's being called E3 is one of that infinite family of beach ball tilings of the sphere. Over here, we have a tiling of the Euclidean line. So if you think about the Euclidean line being tiled by reflection, that's like when you're standing in a bathroom and you have a mirror in front of you and behind you, or in an elevator with a pair of mirrors. It just infinitely bounces the image back and forth, back and forth. So that's tiling the Euclidean line. So that's called affine A1. This A1 tilde is diagrammatically representing that image. And then in this row, we'll see the kaleidoscopes that we saw, the 60 degrees equilateral kaleidoscope, the 45, 45, 90 kaleidoscope, and the 30, 60, 90 kaleidoscope. That's what these diagrams, again, we're not going to go into what these diagrams tell us everywhere. Let me just point out that there's some funny stuff that happens up to dimension 8 in the case of spheres. So these are 8-dimensional spheres. This is a 2-dimensional sphere, so never mind. Once you get to dimensions 9 and higher, it's these pictures, the A, B, and D diagrams just continue. That pattern continues forever. And similarly, in Euclidean space, once you get to 10 dimensions, these A, B, C, D pictures continue forever. So in every dimension, we know exactly what all the possible reflective groups are in Euclidean space or on the sphere, thanks to the work of Coxeter from 90 years ago. Okay, so this is really something that's very well understood, mathematically speaking. Okay? Now, so Coxeter classified all of the reflection groups in spherical and Euclidean space, but there's another geometry. There are 3 constant curvature geometries, Riemannian. Anyway, let me not say words that only these people know. There are 3 geometries, and the third geometry is hyperbolic space. Maybe you've heard of hyperbolic space. Let's talk about hyperbolic space for a second. So this is one of Escher's famous circle limits. This is from 1958, the very first one. And the thing that I want to impart on you is that all of these fish are actually exactly the same size, even though they look like they're getting smaller and smaller. And everywhere you see an angle, like here it looks like this angle is cutting this one by 90 degrees. Those angles are correct. So this is a model for hyperbolic space. Let me try to explain what I mean by that. So here we have the 3 models of geometry. On the left is our 1/2 plus 1/3 plus 1/5, which is greater than 1. So this is the symmetries of the icosahedron. So that's that same tiling that we saw before, moving around. In the middle, of course, is the familiar 30, 60, 90 Euclidean picture, which is just getting pulled back and forth, and everyone's very comfortable with that. On the right is a picture of hyperbolic space with angles 1/2 of a straight line, a 1/6 and a 1/6. The 3 of those add up to less than 1. So in exactly the same way as your brain is these triangles are obviously all the same size. All of the black triangles are exactly the same as all of the white triangles. And I'm not doing anything as I pull this around, right? Look at this picture. The lines are not straight. What looks like straight lines are curved. The sizes keep changing. Is this triangle really the same as that triangle? But your mind has no problem saying, yes, they're all the same. Your mind is so used to this geometry, to the fact that you actually see in 2 dimensions when you see with your eyes. And, well, you have two of them, so you sort of, you fool yourself into thinking that you see a 3-dimensional object. You feel a 3-dimensional object. You know it's there, unless you're Descartes and nothing exists except yourself. Okay, anyway. So your mind is playing all kinds of tricks on you to make you feel like this 2-dimensional image is actually just a very simple rotation of a sphere. But you're so used to it, you don't even notice. So the hyperbolic geometers in the room have the same feeling about this picture. So this picture, all of the lines are straight lines. These are all triangles. All the triangles have exactly the same size. and all of the angles are correct as drawn. So there's a great, Rich and I were talking about this just a minute ago, and it occurred to me that there's a great picture in the office that I was borrowing for the afternoon. All of these boats, these sailboats, including the ones all the way in the back, have the same size. And you have no problems realizing that. You're not fooled by the fact that these look smaller just because they're farther away. So in the same way, what you're seeing in that hyperbolic picture is points that are slightly farther away from our vantage point, from our center point, but they're still exactly the same size. And in fact, the amazing thing about hyperbolic space, Euclidean space, you know that there's not really a boundary here. The page continues, you just can't see it. Right? And we sort of imagine this imaginary plane going in all directions. On a sphere, we know that there's a back to the sphere. We can't see the whole thing, we just see pieces of it. The amazing thing about this model, the Poincare disk model for hyperbolic space, the Beltrami model, is that you can see the entire thing in one disk. So that's why things have to get smaller. You're seeing everything. The entire hyperbolic plane is here in this picture. Okay, so let's go back to Escher. So here again is the same exact thing. All of these fish are the same size. All of these lines are actually straight lines. We're just in hyperbolic space. Yes, please. Okay. So if I look here and I look at what this angle is, if I zoom way into that corner, what I'll see, and you can sort of see it here, this angle, well, maybe this angle looks really thin. It looks like way less than 60 degrees. Or what's this supposed to be? It's supposed to be 36 degrees. So that's distorting the angles. It doesn't bother you because you're used to the sphere. But actually here, none of the angles are distorted. Anytime you zoom in on a picture and you see two angles coming together, those are the real angle if you were standing in hyperbolic space, how you would measure that angle. So this is what's called a conformal. Anyway, the angles here are correct, whereas the angles here are not. Okay, the angles are being deformed. What you would measure if you actually measured this projection would be the wrong angle. Does that make sense? Other questions? Okay, so let's try to understand this Escher. So here are these are black fish and white fish tiling the hyperbolic plane. So some of the mirrors are the standard Euclidean mirrors that we're very familiar with. There's a left to right symmetry in the picture. There's also a symmetry along this line. You can just see things reflect across this line. So those are the usual Euclidean mirrors. Other mirrors are circle inversion mirrors. So what is a circle inversion? So for example, if you look at this line, this is a little piece of a circle. And what does inversion across a circle do? So if I have, this is my mirror, I sort of pulled the mirror out to the side so you can see what's going on. That mirror takes a point P, and if that point is 10 radii away from the center, its inversion is a point that's 1/10 of a radius away from the center. In other words, the image of P is a point P prime that satisfies, like x goes to 1 over x. The distance from the origin is reciprocated. Okay, so the distance as measured by the radius of the circle. So that's what's happening here. This fish is the image of this fish across the circle. And this half of this fish is the image of that half across the circle. Okay, and the entire disk up here, half disk up here, is repeated down here on the other side. And so if we look at this image, here are some more lines of symmetry, mirrors in the circle limit. What we see here is a quadrilateral, and you can figure out what the angles of the quadrilateral are by just counting at each vertex how many black fish there are. So here there's 1, 2, 3 black fish around this corner. So because there's 3 black fish and also 3 white fish, and all the fish are the same, that means there's 6. This is a sixth of a circle, in other words, a third of a straight line. So that angle is a third, is what we would call a third of a straight line. Over here, there's only 2 fish, one on top, one on bottom. So that's a 90-degree angle. So this angle is a third of a straight line. This angle is a half. This angle is again a third. There are 3 black circles, and this angle is again a half. So this quadrilateral with angles a third, a half, a third, a half is exactly the tile that's being moved all over the disk, the hyperbolic plane, to make all of space. Does that make sense? Any questions on how Escher, now Escher was not a mathematician, he just kind of invented this stuff on his own. He was corresponding with Coxeter, by the way. But apparently he says, I didn't understand a word that Coxeter would write me all these things explaining to me the mathematics of what I was drawing, and I didn't understand a word of it. And I just said, oh, that's nice, and kept drawing. So Escher sort of independently discovered this stuff. All right. So why did Coxeter not say anything about the classification of the hyperbolic plane and hyperbolic space in all dimensions? He already understood that the classification is hopeless. You're trying to solve, even for triangles, if you want to understand all of the hyperbolic triangles, what you want to solve is the equation 1 over an integer plus 1 over another integer plus 1 over a third integer is less than 1. But it's easy to make fractions small. You just take whatever, there's no, you just make C to be 1,000 and B to be 1,000,000 and A to be 1,000,000,000,000, and there you go. You get something that adds up to less than 1. So there's kind of no point. The equation is the answer. It's not like here where we have some finite count on our fingers. By the way, I meant to say, the way Coxeter's big classification goes is not so dissimilar to what we were doing here. It really is just keeping track of things in a very tidy way, but it's very similar to this kind of calculation, where you're checking some cases and you're making sure things can close up. So Coxeter already knows that there's this infinite zoo already for triangles that there's no reasonable way to write down what the classification is, so he doesn't say anything. But that's not the end of the story. He left much to be discovered. So the person that picked up Coxeter's story more than most is a gentleman named Ernst Winberg. Now, Winberg sadly passed away. He was still working. He had graduate students. He was in his 80s, but he passed away one of the first people to succumb from COVID in 2020. So he picked up where Coxeter left off, and he constructed many new examples in certain higher dimensional spaces. So let me show you what some of these, and he keeps this formalism of diagrams, this diagrammatic way of understanding hyperbolic space. So for example, this is a 45-degree angle, a 90-degree angle, and an infinite angle. In other words, 1 over infinity, so an angle of 0. So that's this black triangle, and this is the tiling that this picture represents. So this is again a tiling of the hyperbolic plane. He also did things in other dimensions. So this one here is going to be a hyperbolic tetrahedron. So here's what a 4-sided shape in the hyperbolic sphere now instead of a circle, instead of doing things in a disk. If you look in a ball inside of a sphere, this is what a hyperbolic tetrahedron, ideal tetrahedron looks like. And lots of other pictures like this. So Winberg constructed lots of examples of such things, and in certain dimensions. And then in the 80s, he discovered something really shocking. If you remember Coxeter's picture, when we had the Coxeter diagrams, there were some funny things that happened in small dimensions, up to dimensions 8 or 9 or something, and then the list completely stabilized. There's only type A, type B, type C, type D, and that goes on forever. What Coxeter realized is, whatever the final classification of hyperbolic reflection groups will be, it doesn't keep going. There's nothing in dimension 30 or higher. In fact, the largest dimension we know is 21 dimensions. We do not currently know of a single example of a hyperbolic reflection group in dimension 22. And the theorem says there won't be any arithmetic ones in dimensions 30 or higher. Moreover, more recent work from about 15 years ago showed that not only are there, so if you remember, we had this, even for triangles, we had this infinite list. Well, if you restrict yourself to these arithmetic lattices, I realize I haven't explained what that is. If you look at the maximal arithmetic reflective lattices, that's for the mathematicians in the room, there are only finitely many. So there's a finite number. At the end of the day, there's going to be a periodic table at the end of the universe. There's going to be a periodic table of every single maximal arithmetic reflective lattice in hyperbolic space. So that's going to be tiles like those triangles and those tetrahedra that I was showing you, that when you fold them around, make up all of hyperbolic space. You just can't, in high enough dimensions, these things don't exist. And in every dimension, there's only finitely many sort of largest, smallest tiles from which you can get any other kind of tile. So these maximal lattices. And people are currently working on trying to finish this classification, including the workshops that have taken place here at ICERM. Now, there's a whole other side to this story that I think I'm going to not delve into because we won't have time for it. So let me stop there and thank you for your attention.
Opposite of hopeless? I mean, at first you said it was hopeless, and now you're saying there is a classification?
That's exactly right. Yeah, hyperbolic space is like the Wild West. We really, it looks hopeless, but then we realize that there is a kind of classification in certain settings. Yeah.
Other questions? What are fractal sphere packing?
Yes, well, that's the whole back half. I can throw up some pictures if you like. So this is a fractal sphere packing. Let me just show you this picture. This is a fractal sphere packing, and the way you construct one of these is by taking one of these hyperbolic mirror groups and taking one of the mirrors and moving it around by the other mirrors. And in the limit, you get these fractal images. And there's a whole, if I had another hour, I'd tell you all about them. And they're a lot of fun, and they're very fascinating. And they have a whole story with arithmetic. There's some whole numbers here that maybe some other time I'll get into. I did promise them, didn't I? Well, there, I've touched on them.
Signal for me to sit down and listen, or I'll open the floor to more questions.
You would never have a demo of one of those hyperbolic mirrors.
All right, you want me to show the movie? All right, let me not give the whole story of what's happening here. There is a whole long story. I'm not gonna. Well, should I tell you a little bit about it? All right, let me tell you in 3 minutes, since I think I stopped 3 minutes. Yes, okay, 8 o'clock, okay, good. So the story of circle packings, in some sense, you can think of as starting, although that's not really historically accurate, starting with Apollonius of Perga. If you take 3 tangent circles, the theorem of Apollonius gives a straight edge and compass construction of 2 tangent circles that fit into these curvy linear triangles that nestle inside. And you can continue that construction forever and get what we now call an Apollonian packing. So this picture, it looks like it's on a sphere. Here I put the Apollonian packing on a sphere in the same way. If you take a light and you shine it from the top of this sphere, then what you see on the ground will be exactly this picture. It's just easier to draw things on the plane because that's the geometry we have to work with on a screen. So let's stick with that geometry. There's a whole arithmetic side to this story, which is that these whole numbers that I've drawn here, they're 1 over the radii of the circles. So this is a circle of radius 1 over 18. This is a circle of radius 1 over 47, 1 over 83, and so on. And the first thing you might ask is, why are these numbers whole numbers? Why are they integers? Why aren't they something else? The fact that pictures like this exist was observed by Sir Frederick Soddy. He's a Nobel laureate in chemistry, actually, radiochemist. And it follows from a theorem of Descartes, although Descartes didn't follow it to that conclusion. But Rich wanted to see one movie. Okay, so here's a theorem. If you ask, in the case of this sphere packing, which Soddy himself built physically with ball bearings and this crazy picture. So again, this is a sphere of radius 1 over 28 and a sphere of radius 1 over 85 and so on. You might ask which integers appear as these inverse radii. And a theorem of mine says that any number which is either divisible by 3 or leaves a remainder of 1 when divided by 3 will, if it's sufficiently large, will occur in here. And we think that this should be replaced by 300 or something. So that's, the state of things. Yeah, what does this have to do with mirrors? So let me skip past this, which is the reflective construction, the inversive construction of this, because Rich wants to see this this image. Come on. So if you follow around these mirrors, you will get this strip version of an Apollonian packing, and that packing can be obtained, here it is. So you can obtain that same packing by taking these reflections into hyperbolic space, and you take the orbit of a single point and you move it around by these reflections, and the limit at infinity is this Apollonian packing. That's the movie you wanted to see. Okay, so that's the 1 minute version of what that would have been. Yes?
What's the radius of the big sphere? If it's for the first ones you showed with the 18 and 27?
Yeah, I don't remember off the top of my head. It is also an integer. In fact, that radius is a negative integer because the spheres, we want the spheres to all be internally tangent to one another. So the outermost sphere has to have the opposite orientation. And that needs to be reflected in its bend. So these are signed radii. So imagine most of the disks are disks where with the interior, here it's the exterior. There's this old, there's an old joke, I have a second for it. There's an engineer and a physicist and a mathematician, as these all go, and they give them, I don't know, 17 feet of fencing, and they say, enclose the largest area you can. Okay, and so the engineer makes a 17 gon, and he knows that that's within 1% of the best solution, so he's satisfied with that. The physicist proves with variational calculus that the best thing you could do with 17 is to just make a circle, and that'll enclose the largest possible area. So that's it. He's won the prize. He has a theorem that says that's the best you can do. And the mathematician just takes 3 little bits of the fencing, and just makes a little triangle here, and goes back to playing with his paper and pencil. And the physicist elbows the engineer. This guy, idiot, doesn't know what he's doing, and said, hey, you're trying to make the largest. You're trying to enclose the largest shape you can. And the mathematician goes, that's the outside. Orientation, okay.
Other questions? I want to ask a question. So the periodic table has, what, 108 or so elements? So the periodic table of all these maximal arithmetic reflection groups, would they have more or less than 108 elements?
That is a very good question. There's partial classifications in low dimensions, which I think in dimension 3, there's maybe 40 of them. In dimension 4, there's maybe 30. In dimension 2, there's, again, maybe 40 or 50. It's probably going to be more, but not by much. It really is around 100. It would be rather amazing. I mean, there's no chance that, yeah. But it's of the same order of magnitude, yeah.
Are there any other questions from the audience? Okay. Well, I want to thank you all for coming. It's really great to have people at our public lectures again after all the last 3 years. And thank you so much, Al.